Speed, comfort, precision. This is the future of transport.
It moves faster than a Formula One car, a white snake of steel slicing through the countryside at 350 kilometers per hour.
It is so stable that a coin balanced on its edge won't fall, even at top speed. But building a machine this fast requires the precision of an aerospace laboratory.
We don't use heavy steel. It's too heavy. We use aircraft-grade aluminum alloy.
The walls of the train are not sheets. They are complex extrusions, squeezed out like toothpaste.
This double-walled design creates a honeycomb structure, rigid, light, and soundproof. It looks like the bones of a...
To join these panels, we don't use fire. We use friction stir welding.
A spinning tool softens the metal through pure friction, mixing the two sheets together like dough. This creates a perfectly smooth seam. Regular welding bumps would cause drag at high speeds.
The floor, walls, and roof are stitched together to form a tube 25 meters long. Precision is critical. The entire 25-meter body cannot deviate by more than 1 millimeter. Zero margin for error. Before painting, the entire shell is hand-sanded to aerodynamic perfection.
Before the luxury interior is installed, we must kill the noise. The inside is sprayed with thick, damping foam.
Paint is not just for looks. It is a shield against weather at 300 kilometers per hour.
5 coats are applied. Each one is baked in a giant oven until hard as porcelain. The windows are installed. They are not ordinary glass, but thick laminates designed to resist bird strikes.
Now, the defining feature. The nose. It spans 15 meters, shaped like a duck's bill.
This shape is not for style. It prevents a sonic boom when the train enters a tunnel. Machines cannot form these complex curves. The nose is hand-beaten by master craftsmen. Thousands of hammer strikes create a seamless, flowing curve that computers struggle to replicate.
Once formed, the nose is welded to the driver's cabin. It becomes the face of the train.
While the body is light, the legs must be heavy. The bogies. The wheels are forged from solid, high-carbon steel. They must survive billions of revolutions. Massive electric motors are mounted directly to the bogies. No engine, just pure magnetic torque. The suspension is not just springs. It is an active computer-controlled system.
It tilts the train into curves like a motorcycle, canceling out centrifugal force.
The finished bogies are rolled under the levitated train body, the marriage of chassis and hull.
Now, the nervous system. Kilometers of fiber optic cables are laid under the floor. The pantograph is installed on the roof. This is the only connection to the power grid.
It must maintain contact with the overhead wire at 300 kilometers per hour without sparking.
Inside, the seats are not just bolted down. They are mounted on floating rails to absorb vibration.
The windows are fitted with electronic dimmers. No curtains, just liquid crystals.
The driver's cockpit is installed. It looks more like a spaceship than a train.
Every gap is sealed. The train is pressurized like an airplane to prevent ear popping in tunnels. The cars are coupled together. The gangway connections are smooth to prevent air turbulence.
Finally, the train is powered on. The headlights cut through the factory haze. It is alive.
Before it hits the tracks, the design fights the wind. Scale models are tested in a wind tunnel.
At 300 kilometers per hour, air becomes as hard as a wall. The nose must slice it.
We test the suspension on a hydraulic shaker rig. It simulates the roughest tracks imaginable.
The train must be waterproof. We subject it to a hurricane-force monsoon simulation.
Inspectors check the seals with UV light. Not a single drop is allowed inside.
The factory doors open. The finished train rolls out into the sunlight for the first time. It is towed to the high-speed test track, the quiet before the storm. The pantograph rises. 25,000 volts of electricity surge into the motors.
The Hispanic male driver pushes the throttle forward. The acceleration is smooth, silent, and relentless.
Outside, the world blurs into streaks of green and gray. The train reaches cruising speed.
Inside, passengers sip coffee without a ripple. The active suspension fights every bump.
At 350 kilometers per hour, the landscape is a liquid blur. Suddenly, a tunnel. The long nose dives into the darkness.
Inside the dark tunnel, the cabin remains dead silent. The pressurized seal holds firm.
Now, the ultimate safety test. The emergency brake.
At this speed, steel brakes would melt instantly. We use magnetic resistance. Large caliper brakes clamp down on the wheel discs as the speed drops. They glow bright orange.
The train comes to a halt from top speed in less than 90 seconds. Safe and controlled.
But nature is the real enemy.
In winter, the nose acts as a plow, smashing through heavy snowdrifts without slowing down.
Night falls. The train becomes a streak of light, cutting through the darkness.
It approaches the station. The computer calculates the braking curve to the millimeter.
It stops. The doors align perfectly with the platform markings. Google VO3 prompt. Close-up of the platform floor. The yellow safety...
The doors slide open. A rush of cool air and the smell of a new machine.
From a pile of raw aluminum ingots to the safest way to travel on Earth.
Speed, comfort, precision. This is the future of transport.
The bullet train. Google VO3 prompt. Final outro. Like and subscribe for more heavy engineering.